Hi, welcome back to the breadboard and another edition of Raspberry Pi videos, again with Windows 10 for IoT. This time we're going to look at something a little different. Instead of digital to analog, analog to digital converters and things like that, we're going to have a look at some graphical displays. So to kick things off, I'm just going to show you the user interface right off the bat that we have for this. So you can see, if you can guess, which hopefully you will, what we're going to be playing with. So I've just started the application. Here we go. It's my splash screen. And here's the UI. So you can see from this right off the bat that, well, it says it right in the top. I'm written a program in a library to have the Raspberry Pi talk to a pair of 430 Boost Sharp 96 Launchpad booster packs from Texas Instruments. Now these are based on the LS013B4DN04 display from Sharp Electronics, and they feature a 96 by 96 square aspect ratio display. They're about 1.3 inches or so across, and they're a SPI interface connected on them, and they are ultra low power. You're talking microamps of power consumption between updates. So these would be excellent devices for battery powered operation and things like that. And they feature, when they're on black mode, when the display is at what they would call black, it's very silvery, reflective. It has an extremely high contrast ratio, and you're going to see a bit of that when we get to looking at the actual physical displays. For now, what I wanted to quickly do is walk you through the UI before we go look at the physical thing, just so I can tell you what features we have. So right off the bat, we have two main displays. Now these are actual, these are physically look exactly like the real displays we have, and I've put some text on here. Now this text on here, you can actually edit it. These are text boxes superimposed on top of the graphical displays, and if you change this text, you can actually, it'll do spell checking and things like that, because it's a Windows 10 IoT text box, and when you edit in them, it actually automatically puts spell checking and things on for you, which is kind of cool. When you've edited this and you want to send it to the respective display, you just click the update button, which is here. It's just connected to an event handler. Same thing goes for the other display. You edit the text here, you click update, and it'll send the text to that display as well. Now you don't have to edit the text. You can just click the update, and the text that's already here will go out to the display. The fill ones, what that will do is it'll fill the memory buffer with all ones, which effectively makes the display go white. So it's the lightest shade of here. Filling the display buffer with all zeros makes the displays go black. The demo button here will actually run a rolling demo across the two different displays, one pass. But if you click the loop checkbox and turn it on, then it will continuously loop around the different checkbox. If you click the loop checkbox, even if it's during the running of the demo, it will start looping through the numerous display demonstrations that have been programmed into that function, and you can change the timing between the loops by just sliding this slider across. The connections for the displays are shown here. This is just a static image. For the two displays to be connected to the Raspberry Pi only takes a total of 6 connections, and 2 of those are for power. You've got 3.3 volts in ground. We only use the SPI output connection, MOSI, and the clock, and then we have 2 chip selects. Now, because these displays actually use an active high chip select, not an active low, I can't use the standard Raspberry Pi CS0 and CS1 for the chip select. So I'm actually using GPIO 5 and 6 instead, and I'm just ignoring the CSO and CS1 lines, and that works perfectly well with the program. You don't have to use those 2 lines. They're just automatically taken care of for you. Now, when you edit these boxes, what happens is you're actually editing into a in-memory display buffer. It represents the 96 by 96 pixels, and when you hit update, it transfers that into a byte array and then sends it out in a single shot out to the display devices. And one of the benefits of doing that in a single shot rather than each byte by byte with a SPI interface is it'll go out very, very fast. And as you'll see in a minute, the display refresh rate is very fast considering the devices that we're using here and the experience that I've seen up to now trying to talk to D2A ADD converters using the Raspberry Pi. And one of the benefits, or one of the reasons for this, is that the library for the Raspberry Pi and the Windows 10 IoT, the write SPI function will take, so far I've tested up to about 2,000 bytes as a single write command. So it just takes a byte array of an arbitrary length. I haven't tested the limits of it yet. And it'll output it to the SPI device in blocks of 16, but with very, very short delays between each block. And I'll have a look at this on the Tektronix oscilloscope using the SPI decoder later on. But anyway, you'll see that it can actually output it very, very quickly. The other thing I've got here is a bunch of the different functions that are available, things like line draw, circle, rectangle, and I can actually write to the matrix fonts as well. So I've only got a single font as far as an array is concerned, which is an 8x6 font, but you can scale it up by sliding this big slider anything up to ×9, which basically gives you about 1.5 characters on the display if you do it that size. But you can do it, and all you have to do, and I'm just going to do this now while you're watching, is literally take the slider here and just slide it across. And the displays that are on here will already make a representative increase. It's not perfect as far as what you see on the screen up here compared to what goes on the LCD display, because this is, you know, it's rendering on a screen with a Windows font versus a pixel based, and I didn't want to go to the effort of actually making the display screen a 96 by 96 pixel screen as well. So it's just a rough representation. But whatever font size you pick here, up to 8, it will actually output the representative scale. So it's an 8 by 6 characters wide, 8 character high font. So if you're doing 8 as a font size, then it's going to be outputting 6/8, so 48 characters wide and 64 characters down, 8/8 to 64. On the screen. So that's pretty cool. And when you're programming it, and when we have a look at the program, you'll see that it's very easy to pick what font size you want to be able to do. And you can actually mix the fonts as well. The whole screen doesn't have to be the same font size. And when I run the demo, you'll see that it is not the case as well. The other one which I mentioned slider-wise is this one, which controls the loop speed. Now this is in milliseconds, and it will take you between 1 millisecond per demo type up to about 2 seconds. So if you really want to see how fast it can go, take it down to 1. The reason I limited it to 1 rather than 0 is because you basically lose the responsiveness of the program, because I'm not doing it asynchronously, and because I've got a 1 millisecond sleep timer in, all of the buttons and the checkboxes still work, so you can stop it running. Obviously if you're running it not in a loop, then 0 would just quickly blat through it and you'd be fine. But if you're running in a loop, you'd never be able to undo the checkbox to stop the program from running. So I left it as a minimum of 1 millisecond. What else is on here? I think that's pretty much it. I think the thing to point out with these Sharp LCD displays is that they are 96 by 96 square, and I've already mentioned that, but the memory for the display is actually it's 1 bit per pixel memory, and the pixel itself is the actual memory. You cannot read from it, you can only write to it. And when you write to this, you have to write an entire line in one go. Now what I'm doing, rather than trying to write one line at a time and figure out which line has changed, I'm using a memory buffer to actually draw the display, and then I'm sending out the entire display in one SPI write cycle, and it does it very, very quickly. I haven't actually physically timed it, but maybe when we get to the oscilloscope later, we can see how long it actually takes to do that. And As I say, the left-hand display is using chip select 5 and the right-hand display is using chip select 6, or should I say GPIO 6. And that's pretty much the display, or the user interface. So let's go have a look at the hardware. Hi, it's me now. Normally I get myself on the screen right at the beginning. So this is the actual display that we're working with here. It's a little thing. It's a Texas Instruments booster pack. Like I said, it's the Boost Sharp 96 little thing, and that's all it is. It's got a little bit of buffering there if you're running it off of a different power supply, and most of the circuitry in the back here actually isn't used. It uses a SPI clock, MOSI, which is the output SPI data from the CPU, and plus 3.3 volts and 0 volts, and that's pretty much it, except for the chip select, of course. The difference, as I mentioned earlier, with these devices, which threw me a little bit when I first started looking at them, is even though they're a SPI device, they've actually inverted the chip select from the normal expectation. So instead of a low-level chip select, it's a high-level chip select. So the Windows 10 for IoT on the Raspberry Pi doesn't allow you for specifying the polarity of the chip select line. So I basically had to abandon using CSO CS1 and drive the chip selects myself directly, and that works just perfectly for what this application is trying to do. And one of the nice things about that is it actually gives you a lot more flexibility if you want to put a lot more devices onto your Raspberry Pi than what the normal 2 chip select lines actually allow you to do. And I hadn't really thought about it before, but with the design of either whether it's in Raspbian under Linux or whether you're doing it under Windows 10, they only have 2 chip select lines by default, and you really can't add any extra ones, not at least that I've seen. Maybe it comes as a later feature, but you can't at the moment. So by ignoring those 2 lines, I mean, if you're using them because you've got a low-level chip select, then great. But a lot of people started thinking that that's it, you can put 2 devices on. But really, you can just ignore them and start extending it. Now, the thing to remember if you do that, of course, is that when you're writing to other devices, you still have to tell the software that you're using one of those first 2 chip selects. So if you do extend it, you can't use the original CSO and CS1 because they will be the devices that are hooked up to them will be receiving the data as well. So you just need to think about if you just need the 2 or if you need inverted signals, then you can it's just about making choices. Anyway, as I said, that's the display, and the Adafruit has a similar breakout for this Sharp display. It's not in a booster pack format. It's just got the lines hanging off the side that you just plug into whatever microcontroller, whether it be an Arduino, a Raspberry Pi, or something else. And it will work just as easily with my software that I've written without any issues, because as I say, it's just SPI connected. So the hardware itself, this thing does not care. And there's a few there's a few things you have to pay attention to with these displays because of the nature of what they are. And one of the key things is that they can actually build up a bias voltage, like a static almost, on the display. So if you put an image on here and you leave it there for a long time, maybe an hour or 2, without alternating the bias voltage on the display, it can actually stick there. It's a little bit like the old CRT monitors and things, where if you left the same image, it would burn an image on it. Fortunately, with these, it will go away once you start using it again and changing the displays. But it is a little bit annoying if you're not aware of it. But the fix for it is very, very easily. And what I've done in my software is I've set up a 200 millisecond timer under interrupts that just calls a function to send out the command to alternate the what they call VCOM bit, and it's just a 2-byte command that gets sent to the display, and I'm just doing it 5 times a second. 5 times a second. You can do it anything from about 60 times a second down to 1 or 2 seconds between them. It really depends on how much power you want to save. The more you do it, the more energy it will use, but you're only talking about a few microamps versus a couple of hundred microamps. I mean, it's in the scheme of things, it's not a lot. And compared to how much power the Pi is taking on its own when it's running anyway, it really is insignificant. So, I wouldn't worry about what speed you use. I just happened to pick 200 milliseconds just because it was a handy figure that wouldn't overload the performance of the machine or anything like that. So, anyway, let's go look at what I built to test this thing out, and we'll run you through the demo. So, what I have here, of course, is your standard Raspberry Pi. And I've got the 6 connections coming out. These 2 are the chip selects for each display. I got the power. I've got the 3.3 volts with the red one. The black one is the 0 volts. The gray line is the master out, slave in. So that's the data output from the Raspberry Pi. And the purple line is the clock going to the display. And then on the other end, on the display here, what I've done is I've created a little strip board here. Put some feet on it just to make it stand off the bench and everything. Standard little 20-pin, using the standard sockets that you get to just have something to push these displays on so it's not permanently mounted to the strip board, and a little bit of simple wiring. I'm just going to pull one of these off. I wouldn't normally recommend you do this. Actually, I'm going to show you. There you go. So you see it's just these little pin connectors here, and it just pushes on. So it's basically the same as a Raspberry TI Launchpad connection. And the connections at the end, I just put a socket at the end here to take all the wires from the Raspberry Pi to make it easy. And what I've done is it's got pins on the bottom, so they go right through, and it's got sockets on the top. So depending on what I'm wiring to, things like a Arduino that has sockets, I can use a pin-to-pin connection for the top, and if I'm using it to the Raspberry Pi, I can use a socket-to-socket if I wanted to. And I put these little feet on here just so that I can tilt it for the display so that you can see it running on the screen here on the camera. So let me just stop the app and restart it again because I deinitialized the screen there. Okay, just about to start the app up, so I just zoomed in on the display so that you can see what happens as these things power up. As I said, they're highly reflective, so I'm not sure what it's going to look like yet, and I may have to adjust them once we've started. But let me just start the app now. So it's just powering up. And there's the 2 displays right off the default. And what you can see here is that when I initialize the displays, and we'll go through the code later, I can actually output a string to be able to be displayed on the initialization for each display, and I can specify the font size and also the color, whether I want black on white or white on black. And as you can see here, I've got the 2 displays and I've got different on each one. And based on this light, as you can see, the black with the white is a lot more readable than the white on the black. And it's, as I say, it's not really black, it's more of a silvery color. As you can see how reflective it is when I have my pointer here just in the screen, just reflecting off. It's quite reflective. So anyway, that's them powered up. Now I'm just going to click the demo button. It's set for a looped step time of ½ a second right now, but I wanted to give you an idea of how quickly these can update the screen. So I'm going to click it now. All right, that's one pass through. Now I'm going to stick it on a loop and speed it up a little bit. When it's running through this demo, it's actually randomly picking which screen it writes to. That's why it kind of flips around between the 2 here. You can see on the right hand side on that one, it's got quite a big font and different size fonts. And here it's just showing the same thing being shown as it, and bringing up the font and different graphics and various things like that. Each of these displays, these are not saved images that I'm just simply streaming up to the displays either. I'm actually drawing every character, every line for each display before I send it out on the SPI bus to the displays. So I'm drawing it in memory. I'm then basically taking that memory, which is a 2-dimensional array, and I am serializing it into a byte array and then sending it out to the SPI bus in one go. Now in memory, as I'm drawing, of course, this is all vector-based drawing and everything else. So I have line draw routines, horizontal, vertical, circles, arcs, and all sorts of things. And I'm going to post all of the code online so you can use it as you like for this. I think it's going to prove very, very useful. And I got a lot of inspiration from Adafruit, from Texas Instruments. Over the months and years, I've picked up little libraries of different graphics things from all over the place. None of them were specifically written for this, but they did provide me a lot of insight into how to get this up and running properly on these displays. And obviously this is all written in C#, and I had to make it work for these displays in the way that these are put together, because they have some nuances, and when we go through the code you'll see what that is. I think one of the biggies that these have is the fact that the display addressing is actually backwards. When you output the data, the least significant bit is on the right of each byte, and the most significant bit is on the left, which is how you would normally think about it. But when you actually address the rows, the rows coming down, so 00 is top left and 96 is on the bottom, and then 0 is on the left from a pixel base to 96 on the right. But when you're doing the addressing as you come down here, normally you would think you would have 01 for the 00, 01, 02, 03, 4, 5, 6 coming down here. But it isn't. You actually have to output 80 for the first line, or 00 for the very top line, then 80 for this first line, and then you output 40 for the second line and C0 for the third line. So the bits are basically swapped for the addressing. Don't ask me why they did that, but that's the way it works. So a few little nuances like that to output this onto the display when you're driving it that you have to take care of in the code. But you know, it's all done already, and you can see how I've done that. And the other thing that you will see is that there's some optimization in the line drawing routines and things like that, where I don't draw everywhere. I don't do every single pixel a dot at a time. If I've got a long stretch of all ones or all zeros, then I'll actually output a byte at a time for that, instead of drawing each pixel, to try and make it faster. And that's something that even Adafruit's graphics libraries, they didn't invent those things. They took the algorithms from some people that a long time ago did, and they adapted those algorithms to work with their displays. Now, they've done a great job with their displays, don't get me wrong, but a lot of the original work is not theirs. They've just taken it and adapted it. But then isn't that the same for most of the software that we all use these days? Anyway, I think that you've seen that running slowly for long enough. I'm actually haven't speeded it up yet. So let me just speed this up so you can see how quickly it'll go. That's now running. I don't know if the camera's even going to be able to keep up with that. But that's the exact same displays, and I'm now running it at 1 millisecond between each page. So you can see that even though it's under Windows 10 for IoT on a Raspberry Pi, and it's coming out of the SPI bus, and it's doing all of the calculations for every single dot and every single line and every single character, it's able to get some pretty impressive performance out of this. So I'm going to slow that back down again a little bit. That's down to about 1 second per, just over 1 second thereabouts. So that's now 1 second between each hop. Now I'm not outputting the display. I'm not flushing the buffers out to the display for every single pixel that I write on the screen. That would be just silly. What I'm doing is I'm drawing the screen that I want, and when I've drawn the particular screen that I want in memory, then I serialize it out to the screen via this SPI bus. So the actual update on the screen is almost instantaneous. And as I say, we'll do a timing a little bit later, or very shortly anyway. So that's the rolling demo. I'm going to stop the demo from running now because it's getting a little boring, I'm sure. All right, so that's just stopped. So I'm just going to click the fill ones to clear the displays. And you can also, by the way, fill zeros, which puts them up into like a mirror mode. And if I just show you this, you can see how shiny these displays are. They are literally like mirrors. All right. I just sit that down again so you can see it. So what I'm going to do is, I showed you before these two displays that were on my UI, and I'm going to, on the left one, it's got hello and welcome to the display 1. You can have up to 144 characters at the ×1 font size, which is a 6 by 8 font, which gives you 16 characters by 12 lines. And when you edit this box, it even does spell checking, ... nice, etc. So I'm just going to click update, and you'll see how quickly it comes on the screen. Click. Right? pretty instantaneous, which is not bad at all. Now if I say fill zeros, do I do that? No, other one, fill ones, and do the update. You can see it flips the bit, and I've told it to do a reverse video on it. So it's a little bit easier to read. The other one has different text on it, and I'll output that, and there you go. Now obviously because of the way that's working, I haven't, if I filled the screen, it's only written the lines that I actually told it to write, so it's not filling in all the blank ones. But if I tell it to fill zeros first and then do the updates, right, it's clearing out my blank lines. Yeah, maybe a minor bug in my text writing. That one's fine. This one's got, it's because it does actually have blank lines in it, so that's probably why it's doing that. I'll have to look at that. But anyway, immaterial. Doesn't detract from the demonstration. If I change the font sizes, so I'm just cranking up the font sizes on the screen here. I'm up to a font size of 4. So if I just then send the updates, you can see it outputs them much, much bigger on the screens. And I'm just going to actually click in the right-hand side one and type in it using the keyboard that you saw before. And I'm just going to say, hello, Peter. And I'm going to send that. And it's in a 4-point font. All right, so there you go. It's a little bit too big to get it on the screen, so I'll shrink it and send the update again. Not quite fitting, so I'll go a little bit smaller. And there you go. So it's not quite, just because of the spacing, it's not quite fitting onto. Yeah. The hello is actually one full line. It's not quite one full line on the top screen. The other thing you can do with this too is, of course, is you can put in things like /n and force different text on the screen. So if I put in hi and then a \n for a new line, and then put in you, and I just send that. So it's got a just send the update. You'll see, of course, I did my slash the wrong way, which is why it's showing up instead of cleared away. Just clear that out and do it again. Oh, of course it's not a character return. I'm trying to type it on the screen, and it's it's taking as 2 individual characters. On the screen I need to literally type the return key. So all right, just send that instead. There you go. Okay, so if I just try something a second, clear the screen and send that update. Yeah, I haven't cleared out all the text off of the buffer, which is why it's doing all of that. Yeah, so there you go. Sending out text to each screen, send update to that one, clear them both out, send the updates, that rewrites, send the updates to that one, and that one rewrites the little bit of text that I have sent to it. What else to demonstrate to you? I think that's pretty much it. I haven't put on the graphical display any capabilities to do your own vector graphics and all that kind of stuff by typing on the screen. You could do that with a text box and things if you wanted to. I haven't for this demo. I just wanted to show you that it's relatively straightforward to get these displays up and running. Now I say relatively straightforward. It's probably taken me quite a few days writing the libraries and adapting things and getting it all up and running and figuring out the little nuances. But now that I've done that, of course, you can share in that knowledge and get your displays up and running a lot quicker. And the techniques I've used for this, you can actually adapt for any other display as well, as long as they've got an XY coordinate-based plotting scheme, and you can output the data in a big chunk to the displays, and there's no reason why you couldn't do much bigger displays and color displays and things like that as well. So I think now it's time to go have a look at the code. That's pretty much the demo, and as you can see, like I said, has got all of the features, line drawing and everything else in there, that works quite nicely for both displays and will I think serve you for doing your different projects. Like, I intend to use these displays for maybe my power supply project or something like that. So as you can see, I could easily put voltage and temperature and current settings and readings from an ADC and stuff like that onto this. If you had some other thing like maybe a house temperature controller or a distance sensor for a robot or anything like that, you could equally well have your display being put onto one of these kind of things. And they work very well, and as I said, they take very, very little power. So let's go have a look at the code.